Michael Peskin received his PhD from Cornell University in 1978, studying with Ken Wilson. He did postdoctoral appointments at Harvard, at Saclay, and at Cornell. And then he joined the staff at the SLAC National Accelerator Laboratory at Stanford, where he's now professor of particle physics and astrophysics. He's worked on many aspects of quantum field theory and elementary particle physics, but much of his work has centered on searches for new physical interactions through precision measurements at high-energy colliders. And of course, to physicists of my generation, he's well known because he taught us all quantum field theory through his textbook with Daniel Schroeder. So I still have my copy signed by him when I was a young, starting wide-eyed graduate student. So he will tell us now about searching for new physics using precision standard model measurements.
Okay. So I ended the last talk with a question. Shouldn't we believe that the standard model is exactly correct? I now have to give you an extended introduction before I begin the actual meat of this talk, that I strongly believe that the answer to this question is no, despite the beautiful experimental confirmation that I just described in the previous talk. And so let's discuss that a little. The standard model works extremely well for basically all high-energy processes. Those of you who've been following the LHC experiments are really amazed that the standard model can actually calculate correctly the cross-sections for things like proton-proton producing a W plus n jets, where n is as large as 5 or 6. So those are calculations that involve, at the one-loop level, literally millions of Feynman diagrams, and they all add up to the right answer. However, the standard model is conceptually incomplete, and I think this is well appreciated. It cannot explain, in fact, it is incapable of explaining the spectrum of quark and lepton masses, the origin of the matter-antimatter asymmetry of the universe, and the existence of dark matter. And you can add your own things to this list, but these are three things that are extremely striking. There's a numerical analysis book that I like very much by Hamming, where he says the motto of the book is, "The purpose of computing is insight, not numbers." For the standard model, the numbers work, but the insight is not there. And as a theoretical physicist, I think this is something that we have to take extremely seriously. Actually, most importantly for me is a defect of the standard model that was not mentioned on the previous slide, which is the fact that the standard model cannot explain the phase transition to a ground state that breaks SU2 cross U1. Here is the full explanation for spontaneous symmetry breaking within the standard model. Number one, the most general renormalizable potential for the Higgs field is given by this expression. And number two, for some reason, mu squared is negative. That's it. That's all the standard model gives us. And I hope you agree with me that this is totally inadequate as a theory of physics. We need to be able to dig deeper to explain certainly what is one of the most profound phenomena in the universe. You folks all know that this statement here is also very problematical. Mu squared receives large additive radiative corrections, and actually the corrections have both signs. So it's not obvious which way those corrections will eventually pull the final value, which is close to about 100 GeV squared. Sophisticated people call this the gauge hierarchy problem. I really don't like that terminology because I think that this is not a problem that has to do with grand unification or very high scales. It has to do with the fact that we have no clue what the real physics is of this phase transition, and it's something that we need to find out. Now, this is very much in contrast, or maybe has an interesting relation to phase transitions in condensed matter, such as, for example, that in superconductivity. So actually, there's a strong analogy to the theory of superconductivity. In 1950, after many years of the existence of superconductivity, Landau and Ginzburg proposed a phenomenological theory, and as you all know, the work of Higgs, Broughton, Engler, and Guralnik, Hagen, and Kibble was really based on copying that theory and showing that it solved the problem of giving masses to spin-1 particles in particle physics. That theory was fantastically successful. It explained the thermodynamics of the phase transition, the critical magnetic field, the presence of type 1 and type 2 superconductors, many other phenomena. However, the thing that it couldn't do was to explain why superconductivity occurred. That was left for the future, and in fact wasn't solved until 1957 in the work of Bardeen, Cooper, and Schrieffer, who showed how electron pairing actually was achieved mechanically through atomic physics. Now, I think in the electroweak phase transition, we're still in the Landau-Ginzburg era. And it's a big question for us how we can get into the BCS era, where we have a fundamental understanding of where the Higgs potential comes from. Actually, superconductivity is not the only example. All phase transitions known in condensed matter physics have fascinating physical explanations. Here's one of my favorite examples. This is a nematic liquid crystal for which the patterns correspond to the alignments of this kind of molecule, for which the molecules like to align at a temperature which is sufficiently moderate. I think it's myopic to think that the Higgs phase transition in the early universe does not have equally fascinating dynamics, which, however, we have yet to explore. Okay. However, all we've got today is the Standard Model. To make a theory that explains the Higgs potential, we can't do that with the ingredients of the Standard Model. There just is not enough there, as I've already emphasized. So we need new particles and forces beyond the Standard Model. How do we find it? Over the past decades, we've searched for beyond the Standard Model physics in many ways, through direct particle searches at the Tevatron and LHC, through searches for new mechanisms of CP violation, which maybe except for the latest LHCb anomalies has really come up empty, through direct and indirect searches for dark matter. In all cases, a large parameter space of possibilities has been excluded, and we're really looking now at the ultimate limitations of these techniques. So if we want to solve this problem experimentally, by finding new interactions, we need a completely different way to do it. And I think, fortunately, that method is suggested by precision calculation. So I'd like to discuss in this talk a perspective on the search for new physics through precision calculation. I've already explained that the Standard Model is in excellent agreement with current data, and the flip side of that, it means that we have excellent sensitivity to possible new physics effects. The unifying principle that I'd like to use to discuss this in this lecture is the idea suggested by the LHC exclusions, that whatever new physics we're looking at is at a high mass scale m compared to those mass scales which we've currently been able to probe. We can, in this case, under this assumption, we can parameterize these new interactions in a systematic way. And the way to think about that is to integrate them out, consider them as modifications of the Standard Model. Now, the Standard Model is already, as Weinberg and Nanopoulos pointed out in 1994, the most general dimension 4 Lagrangian with SU3 cross SU2 cross U1 gauge symmetry and the today known particle content. So any new effects from beyond the Standard Model can only be seen if they contribute higher dimension operators to this structure. So what we'd like to do is to think about adding to the Standard Model new operators of dimension 6, dimension 8, etc. If we can see the signs of those new operators in experiment, that would be the discovery of new physics, which then we can try and relate back to the problems that I've just described. Dimension 6, by dimensional analysis, gives effects of mz squared over m squared. Dimension 8, mz to the fourth over m to the fourth. So these effects are necessarily small. If m is a TeV, this is the percent level. However, if we can reach this level, we really have the possibility of learning something genuinely new interactions that do not exist in the standard model. There's a theoretical foundation to this subject that I don't have time to describe, but I'd just like to cite two really foundational papers. The first is the paper by Ken Wilson, which included this operator dimension way of analyzing physics. The other is a paper by Steven Weinberg, which is very beautiful, where he explains basically how to actually carry out calculations in a, quote, non-renormalizable theory, systematically using dimensional regularization. Actually, these two people were big influences on me early in my career, and it's nice to cite them on the same slide. Now, given the foundation, we basically, you might say, just turn the crank, although some new ideas are actually also required. Okay. The first example, which is maybe the easiest one, is the study of the compositeness of the electron. This is a subject that was discussed very early not so early in this history, but early compared to now, at the 1982 Snowmass workshop. And it was noticed by Eichten and Lane and me that if the electron is composite, we would expect strong interactions at the scale of the compositeness, at the scale of the electron radius. And you could parameterize those by adding some dimension 6 operators that would represent essentially electrons coming together, exchanging constituents, and going off. So instead of the usual gamma and Z exchanges, we would add a strong interaction contact term, parameterized in this way. And actually, if you analyze it, there are only 3 possible operators there, which are the 3 possible products of currents that you can apply. Well, this is a very simple theory. You recompute Babi scattering. I should have also included the T-channel diagrams. With these calculations, you compare to experiment. At that time, the best experiments were 30 GeV in the center of mass, and you see whether this contact is visible. There's a little advantage because these diagrams are of order alpha, whereas this one is 0th order in weak couplings. Actually, LEP2 carried out this study and set very strong limits, 8 to 10 TeV, depending on exactly what combination of these eta parameters was assumed. I think you can fit with 3 eta parameters and get a limit that m, in complete generality, is above 8 TeV. This is a very strong limit. This corresponds to an upper bound on the radius of the electron of 6 times 10 to the minus 19 meters. That number's probably smaller than you would have guessed, just naively, but that's the limit. Actually, the LHC limits on quark compositeness are only comparably strong, maybe a few times 10 to the 19, and they're also model dependent. Because in that case, unlike the case of leptons, there are 17 operators, and typically the fits only include one of them. So one should take that into account in comparing. This is LHC at 13 TeV. This is LEP2 at 200 GeV. So the restriction and the leptonic nature can be very powerful in making these precision tests. There's another historical example, which is the so-called oblique corrections, which are corrections to the precision electroweak theory that I described in the previous talk. Some time ago, Brian Lynn, Stewart, and I made the following observation. In many models, and in particular in models that directly are relevant to theories of the Higgs potential, you introduce new particles whose coupling is strong to the heavy particles in the standard model, W, Z, and T, but is weak to the light particles in the standard model, like electrons and light quarks. In that case, new physics appears in vacuum polarization diagrams that couple directly to W and Z, but the new physics effects can be ignored in the vertex diagrams, which intrinsically involve the light quarks or leptons. So we call these corrections oblique corrections, and actually Lynn and Stewart and his student Kennedy went off to make the theory that I described in the previous slide, where you enhance this to a truly precision calculation. On the other hand, Takeuchi and I went off in another direction to try and parameterize these vacuum polarization amplitudes and make a general description of physics beyond the standard model visible in precision electroweak. Now, we didn't originally express it in this way, but it turned out that the leading corrections correspond to adding 2 dimension 6 operators. So again, it's an example of this study of new physics through the presence of dimension 6 operators perturbing the standard model. Here's more explicitly how this formalism works. You assume that the only new physics effects are in vacuum polarization diagrams. This is a very convenient parameterization of the electroweak vacuum polarization diagrams. This is the usual photon vacuum polarization. 3 is weak isospin. Q is something that the photon will couple to. And the W vacuum polarization, just for symmetry, I wrote as pi 1, 1 rather than pi plus minus here. Now, each of these amplitudes has a Taylor expansion in q squared over m squared. So once again, we're going to assume that the scale m is large. The vacuum polarization begins in order q squared. Similarly, pi 3q, there's no constant term. In these, there are constant terms. So up to order q squared over m squared, that is up to the order of dimension 6 corrections, there are 6 coefficients here. Now, 6 is very interesting because of the following things. First of all, I told you in the previous talk that there are 3 renormalizations that you have to do, which involve these coefficients. So 3 of the parameters are actually eliminated in favor of g, g prime, and v, or whatever on-shell set of 3 variables you're going to use to define the theory. Then there are 3 left, and they correspond to these combinations, which we called S, T, and U. S is basically the amount of stuff that's in the vacuum polarization. T is the asymmetry between the W and Z vacuum polarizations. U actually has both effects. And it turns out that it's only generated at the level of dimension 8, so it's actually irrelevant in the context that I'm describing. So now we've got 2 parameters, and the most general type of new physics that you would see in precision electroweak under this oblique hypothesis is given by something that you can draw on a plane, which is very cool. And so, and then any observable can be written as a standard model calculation plus some correction linear in S and T. So every measurement makes a line on this plane, and by overlapping them, you can get experimental constraints. So let me show you a little of the history of this. It's kind of fun. First of all, some guidance on the size of S and T is given by calculating for a new electroweak doublet. S is 1 over 6 pi, which turns out to be quite a large deviation compared to the current high precision values. And T depends again on isospin breaking things. Actually, the effects of the standard model top quark and Higgs boson can also be expressed approximately in this framework. And I've written the formulae here. Remember, T depends quadratically on the top quark mass and logarithmically on the Higgs mass, as I explained in the previous slide. And so here's the ST fit that we did circa 1991. This is the standard model with 2 values of the Higgs mass. These stars represent various values of the top quark mass. So you can see that the constraint that I gave before, that the top is between about 120 and 180, would correspond to this region of the allowed diagram. So this is actually a determination of the top quark mass. These are some models called Technicolor that probably Steven Weinberg introduced and then would like to forget, and they are excluded by this analysis. Here's the 1998 ST fit, and you can see now how this works. The bands here come from the mass of the W, the Z leptonic width, and the S star, the Z leptonic polarization asymmetry. Those combine to give an ellipse like this. At this moment, the top quark mass is known, so it's fixed, but the Higgs mass is not known. And varying the Higgs mass, you trace out a trajectory in the ST plane like this. You can see the effect I showed you before, that the precision electroweak experiments strongly favor a light value of the Higgs mass. Here was the number given by the LEP electroweak working group in 2008. Here's the ST fit today. And if you just take these slides offline and look at the scales, you can see how it compresses as we know more and more about precision electroweak. Okay. So now, that's all I wanted to say about history. The rest of this talk is about the history that we haven't lived yet, namely the next stage in precision calculation and its comparison to experiment. We've learned so much from the Z, and actually much of the information we have, which are limits on new physics from the Z, are still the best limits, despite everything we've learned from LHC. And so I think it's important now to think about the next logical target of precision calculation and experiment and the use of them to search for new physics, which is the Higgs boson. So we now know the mass of the Higgs boson is 125 GeV. With this parameter known, all Higgs production and decay amplitudes can be predicted precisely. To the extent to which you know this number very precisely, it's now known to about 4 significant figures, and other inputs to the precision electroweak program, you can make precise theoretical predictions that can then be tested by experiment below the 1% level. And any deviation from these predictions would be a signal of new interactions beyond the standard model. So the precision study of the Higgs boson really gives us a new approach to the discovery of that new physics that I've argued is there, but so far we have no evidence for it. Maybe I should say the verification or exclusion of these predictions is the unfinished business of the standard model. And so I'd like you also all to take away that even though we're at SM at 50, the standard model's not over. There's one more thing that we have to do, which I'm now going to describe to you. By the way, this is the current determination of Higgs couplings by the LHC experiments, in particular by CMS. The mu parameter is a combination of production and decay amplitudes, essentially the rate of a sigma times branching ratio divided by the standard model prediction. 1 is the standard model, 0 is no Higgs, that's totally excluded in all of these decay channels. The errors here are 20 to 30%. They will get better, although I think there are limits. First of all, I'd like to say there are many modes of Higgs boson decay that are in principle observable in experiment, and actually, as you see from the previous slide, have actually been observed at the LHC. It's interesting that different modes have different sensitivity to different kinds of beyond the standard physics model. I like to paraphrase Tolstoy to say that every exotic model is exotic in its own way. So the coupling to B and tau is particularly affected by supersymmetry and the presence of a second Higgs doublet. The coupling to W and Z is especially sensitive to models where the Higgs is composite. The coupling to gamma, G, and top is especially susceptible to corrections by models of top condensation and new vector-like partners of the top quark. And what's especially interesting is that these corrections cut into the model space in a way that's essentially orthogonal to the search for new particles. So one can cover new phase space that one can't cover just by going to higher energy at hadron colliders. Here's an illustration of the different patterns. So these are 3 very different models of beyond the standard model physics. 0 is the standard model. The deviations are in percent. And you can see that the patterns can be very different depending on what kind of new physics model you're talking about. Here's a calculation recently done by James Wells and Kevin Zhang. It illustrates this orthogonality. The bands are different levels of the Higgs coupling to BB bar. This line is these are all in models, supersymmetry models with b-tau unification. This line here represents the current LHC exclusion. This dotted line, the exclusion expected at the end of the high luminosity era of LHC. You can see that down here, there's all kinds of accessible phase space that we can actually explore using precision Higgs measurements that we can't explore in any other way. There is a problem with this, and that is that unfortunately the predictions of essentially all the models I've talked about are below the 10% level in the couplings, which means that you need very accurate experiments to uncover these predictions and understand that they're there. It's not surprising that these numbers are small, because parametrically the effects are of order mh squared over m squared, the result of adding dimension 6 operators to the standard model Lagrangian. The LHC experiments are projected to reach 5 to 10% accuracy in various decay channels in coupling measurements. And unfortunately, 5% times 3 sigma equals not in the game. So we need a different kind of accelerator to do these experiments. Fortunately, there is one which is feasible, which is to study the Higgs in E plus E minus annihilation. The peak of the cross-section for E plus E minus to Z plus Higgs is at 250 GeV, as we now know from the value of the Higgs mass. And this energy would be accessible to a next-generation high luminosity E plus E minus accelerator. So let me say a little more about the theory. There are some complications to this theory when you really look at it in detail. In particular, deviations in the couplings to B, C, tau, and GLU are controlled, each of them by a single coefficient in the effective dimension 6 description. However, the couplings of W and Z have two possible independent structures. One with the structure of the standard model, one which is a coupling to field strengths, which has a different structure from that in the standard model. So there are two parameters, A to W and zeta W, and for the Z, A to Z and zeta Z. And in a general model-independent discussion of the Higgs couplings, those parameters have to be measured separately and discriminated from one another. Actually, it's a problem to find an appropriate framework to do this. But fortunately, this framework that we've been provided of thinking about new physics as generating dimension 6 perturbations of the standard model actually precisely does the trick. And a full explanation of this is given in this paper by my colleagues from SLAC, from KK, and from DAISY, working together on trying to find the best way to analyze future E plus E minus data on the Higgs boson. There's a problem when you deal with dimension 6 operators in that their number is very large. Actually, for one generation, there are 59 baryon number conserving dimension 6 operators. And when you try and think about the problem here, at first sight, they all come in, and you have to do a fit with a very large number of parameters. But if you restrict yourself to E plus E minus collider measurements, it turns out the number is much smaller. It's only 17. So 17 of these operators contribute to Higgs and other relevant processes, including precision electroweak and E plus E minus to W pairs. In this paper, we demonstrate that it's possible to take the future data from an E plus E minus collider and constrain all 17 of these parameters simultaneously using the large number of observables that are available at these colliders. So I don't expect you to believe that offhand, but please go look at our paper and you'll see exactly how it works. So it's very cool. A completely model-independent analysis is possible within the framework of this effective field theory. And the results, if you put in the expectations, are very strong, as I'll demonstrate in a moment. For example, this is supposed to show you some of these. I think 15 of these operators are listed here. I can discuss that more if anyone wishes. For example, here's the solution to the multiple couplings of W and Z. It turns out that the eta and the zeta parameters are related between W and Z. The C's are different coefficients of operators in this effective field theory description. These two are different, but CT turns out to be essentially exactly the T parameter of precision electroweak. So it's very small, so these two coefficients have to be equal. On the other hand, zetas are related to a particular coefficient CW plus, with correction suppressed by powers of sine squared theta W, to other coefficients that appear in the analysis. However, this one, for example, is strongly constrained by W pair production. So one can get constraints on these parameters that basically make these two parameters very comparable except for an overall value of cosine squared theta W. Finally, the parameter zeta z is very sensitive to the polarization asymmetry in the reaction E plus E minus to ZH, the difference in cross-section with left-handed and right-handed polarized beams. So that's extremely cool. By using polarization, you can disentangle the eta from the zeta effects and solve the whole problem. So again, if you look in our paper there, you'll learn many things like this. It was really fascinating to work all this out. And in the end, you come to the idea that you can really, using the predicted data set for one of these future accelerators, really measure these Higgs couplings extremely well. So this is the precision of Higgs couplings in percent. The red are the projections for Atlas given in this publication. The light green are the predictions for ILC at 250 GeV with 2 inverse attobarns, essentially the current proposal which is on the table in Japan. The upgrade of that to 500 GeV would basically decrease those errors by a factor of 2. And please notice, this level here is the 1% level of accuracy. So for Z, W, and B, you're meeting that criterion, and for others, you're very close to it in a way that's systematically improvable, either with higher luminosity or going to higher energy. So I've told you what the goal is. I've told you the promise. Here I've told you it can really be achieved in accelerators we're thinking about for the next generation. Okay. Now, I hope the organizers will allow me to just take a little more time to tell you a little about my favorite one of these, which is the International Linear Collider. Actually, this is a completely designed machine. The technical design report actually was submitted in 2013. Japan is a consensus-based society, and so this began a long deliberation with all of the possible stakeholders. The Japanese Science Agency basically set up 5 committees to look into every aspect of this. They've met over many years in what I should say is a very opaque process. However, that process now seems to be coming to an end. The final committee reports actually were submitted, I learned when I was in Japan a few days ago. It's now only the last high-level decision that has to be made. There's a deadline, which is that the decision whether or not to go forward with this machine must be made before the European strategy study that's coming for next year. So we're going to learn in the next 6 months whether Japan is going to go forward with this machine. And I'm an eternal optimist, but I think the chances are very high. I just wanted to show you a few things about the recognition of ILC in Japan. This is the Diet representative from the Sendai area who actually came to SLAC last summer for our Linear Collider meeting. Here he's discussing with Paul Granis, you'll recognize, and other people. The next picture, please don't laugh, because it's very serious. This is Lynn Evans, the fellow who built the LHC and who is now the director of the Linear Collider collaboration with Hello Kitty. ILC has industrial partners who introduced LCC to Hello Kitty, And a campaign was started. And you see in the back here, it's Hello Kitty with glasses. She's a scientist. And what she's riding is an ILC cryomodule. Items with this logo are available for sale in Japan, and they've sold 15,000 of these things to Japanese middle school students. So this is a project with high recognition. And as I say, I think the probability that it advances, it's very high. So please watch for news of ILC later this year. I hope that you in the audience will also make clear to others how important this Precision Higgs program is at one accelerator or another for the future of high energy physics. Frankly, I think that given what's happened at LHC, this is really our chance, maybe our last chance, to have accelerator-based high energy physics that can really make an impact on this serious question of where the Higgs potential comes from. As I say, the unfinished business of the Standard Model, which we really now need to understand in detail. The nature of the Higgs boson. Now, one more thing. Other people at this conference will tell you this, but don't let anybody tell you this, that we can ignore the physics of the Higgs field. That's old stuff, and only think about physics at 10 to the 12, 10 to the 16, or 10 to the 19 GeV. That's just hogwash. The nature of the Higgs boson affects how we think about physics at every higher scale. Is it supersymmetry? Is it composite? The models are completely different. And if one model is correct, volumes on the other side just get thrown into the wastebasket. We have to understand this question. It's crucial. And that is a very important message that I'd like to convey here. So, as I said, the Standard Model has unfinished business. We have the possibility of completing this business by making precision measurements on the Higgs boson and making a precise comparison to theoretical predictions that we already have in hand. That can reveal new interactions of nature and give clues to their identity. And I think we should not miss this opportunity to really carry forward accelerator-based high-energy physics. Thank you very much. David. Oh, you need a microphone.
Since you were giving a pitch for the ILC, I must ask you to come, and now it's 250 GeV, to compare that with the CPC at 250 G circular E plus A minus accelerator.
Oh, I'm happy to do that. First of all, I'd just like to say, my attitude in this talk, and it is actually my real attitude, is the following. There are several of these accelerators on the table, and in particular, there are two that could be realized in the near term. One is the ILC, the other is the CPC, the Circular Collider in China. The CPC planning is, if anything, more opaque than ILC. I think I've heard from many people, including Tao Han, that this has to be a personal decision by Xi Jinping. I don't have anything to say about that. As far as the ability to determine Higgs couplings, the abilities of those two machines are roughly comparable. And there's a detailed table in our paper that demonstrates this. Essentially, the CPC is projected to have higher luminosity, but polarization, which the CPC will not have, is also an advantage. When you compare the two, it's roughly a wash. So at that level, the realization of either of these machines would complete the program, at least at the level of the light green bars here that I discussed. Now, the machines have different advantages. There's some people who are not fond of E plus E minus, who say if we build the CPC, we'll then have a big tunnel. We can trash that machine and build a high-energy proton machine for whatever that's worth. I'm of a very different point of view. I think what you really want to do is build a long, straight tunnel that will be the host of linear colliders into the future. High-energy laboratories always expand. They're upgradable in some way. You build the initial stage, you go back and ask for more money, and if you've had success, you get it. That's our history. And so if the ILC at 250 is built, we will have the ILC at 500, which is shown by the dark green. We will have the ILC at 1 TeV. And I believe, although maybe we should carry this discussion offline, that we will eventually have E plus E minus or gamma gamma experiments at 30 TeV. Maybe not within our lifetime, but within the lifetime of people in the back of the room. So we'll see. Unfortunately, this decision is not up to us. It's really the people with the big money in China and Japan and in Europe, which of these will go forward. And all we should say is, well, whatever it is, we want this, because it's very important to us.
So, assuming we have LHC, yeah, assuming we have LHC, and do you see any real advantage to building 250 GeV?
I don't see any advantage to. I mean, there is a marginal advantage. There's a paper by Tim Barklow in which he shows that there are some gains by co-analyzing the two data sets. But personally, I don't think it justifies the cost. However, it's not my money. If ILC goes forward and China would like to compete with that by building CEPC, there's probably enough money in the world to do that if China will make a large contribution. Then we'll have something like Babar and Bell, and we'll have competition. We'll really get to the heart of this. But I'm not putting money out of my pocket to get a second of these accelerators. I think we'll be lucky to get one, frankly.
Okay, if not, let's thank Michael again.